Hello. Okay, now this. Hello. Sorry, we are a bit late. Wait, which one is this? Let's go to presentation slideshow. Okay, should be fine. Okay, can you see the screen? Yeah. Okay. Yeah. So the midterm will be next week. Scheduled. It's a little faster than last year because I want it to be not so far away from our teaching. Yeah. So we finished teaching chapter 4 last time, and the midterm will be on chapter 3 and chapter 4. And it's a bit tight schedule, and hopefully we'll do fine. And also, something else is if you see the website, you see the recording from over last year starting on March 18th. So hopefully we won't go online again this year. Yeah. And that's it. And anyway, so we will start chapter 5 today, I guess. Before we start this, anyone has question on chapter 4? We go through quite a lot on chapter 4. Okay, so the online people probably cannot see, but we can show here really quick. The chapter 4, yeah. So a quick review for people here. Oh, it's going to stuck. Never mind. Okay, not going to show here. Anyway, we stopped. We got chapter 4 last time. It's here. Anyway, we finished chapter 4 last time, and there was convolution property. Wait, can I? Okay, probably not. Yeah, there was convolution property, and it's really fun. And we see from the convolution property that you can look at the LTI system in the frequency domain, and it will be just big H times big X, and that'll give you an easy way to solve differential equation. And also there are some mathematical technique on partial fraction expansion, which is quite fun. And that's about it for now. Any question? If not, let's go to chapter 5. Okay, chapter 5. So chapter 5, once again, is Fourier transform. And not surprisingly, we talk about continuous time Fourier transform. Then now we talk about discrete-time Fourier transform. So this is a big picture, although the tree is a little weird. So we have been talking about Fourier series since chapter 3. So we talk about periodic. So for periodic functions, we have Fourier series and a continuous time Fourier series and discrete-time Fourier series are taught in chapter 3. Then for non-periodic function, and the continuous time, we have the Fourier transform in chapter 4, which has a very nice symmetry periodic property. And now in chapter 5, we want to talk about discrete-time Fourier transform, which is for discrete time, obviously, and non-periodic function. And here is the table for chapter 5, basically similar to chapter 4. And now, before we start deriving our Fourier transform for discrete time signal, let's talk a lot about its similarity to other chapters. So first is spoiler here. So those are the two equations you are going to see a lot in chapter 5. So our, once again, synthesis equation and analysis equation. So synthesis equation, we have x of n is discrete time, and it's going to be an integral over 2 pi of our the spectrum big X. So integral over a 2 pi region, the spectrum big X, and once again is e to the j omega n and d omega. And analysis equation, big X of n is equal to summation x of n e to the manager omega and from minus infinity to infinity. So there are lots of similarity to other things we can think about here. So first is that chapter 5 is obviously going to be similar to chapter 4 because they are both Fourier transform, both are periodic signals. And yeah, they are periodic, so this X range is from minus infinity to infinity. You can see big is you have integral from minus infinity to infinity on chapter 5 and on chapter 4, and on chapter 5 is also the summation of X of n from minus infinity to infinity. But now we have kind of a high level duality, which we kind of see this thing in chapter 3 already. That is, you change x of t to x of n. So you change from continuous signal to discrete signal. Then because x is discrete, so because on time domain you are discrete, then on x domain, then on the frequency domain is big X domain, you will get periodicity. So yeah, this is, although we didn't formally state this, so this is a kind of a duality, also another kind of duality in Fourier series, where you are discrete in one domain, then you will be periodic in another domain. Okay, so we get this periodicity of 2 pi in our big X domain. We're going to see in more detail. And remember, we also see this in chapter 3, where you change x of t from continuous to discrete, then your an get this weird periodicity of big N. But if you multiply big N with omega naught, then you see your AK is periodic with period 2 pi. Okay, so that's similar. And that's fun. And we also have more duality. You can also think chapter 5 stuff being duality. Okay? So this looks nice, but might confuse you. Hopefully you don't get too confused. And yeah, so you can also think chapter 5 stuff being dual to chapter 3 stuff, because you see, well, basically that's a similar form in the equation, because you see in the starting of chapter 3, when we talk about chapter Fourier series, we have x over t being something continuous, and a of k being something discrete. And here we basically switch to the role of t and omega. So now we have x of n being discrete, so that's corresponding to this ak being discrete. And then now we have this being big X of omega. Well, but we actually call it big X of e to j omega for notational reasons. But if you think about this as a function of omega, then since this is continuous and has periodicity 2 pi, and that's similar to chapter 3, where your x of t is continuous but has some periodicity. Okay. So any question? That's yeah. This is quite a lot to think about. So now we can kind of remember there are all kind of duality, and you can, when you have time to study yourself, you can always come back to this page and compare also those things. But for now, it's better to clean up your brain a little bit and focus on the derivation now. Okay, so derivation we are going to follow chapter 4. And so in chapter 4, we derive our Fourier transform from the Fourier series. So we're going to do the same thing. We're going to start from Fourier series and push our period big T to infinity and derive our Fourier transform formula. Okay? And yeah, exactly what we do. So very similar to chapter 4. So we know we have discrete-time signal. Then we can write periodic discrete-time signal. Then we can write it in Fourier series. And now we want to derive the Fourier transform for a periodic signal. So this signal here, a periodic, and we derive the Fourier transform for this by making a periodic signal out of it first. So we just copy and paste this thing with some period n. Okay, so infinite copy paste from go back in time and forward in time. So it becomes a periodic signal, and we are going to take big N to infinity. And in that limit, this new x of tilde will look like x of n. X. Okay? Sorry, this tilde x of n will look like x of n. So yeah, exactly like chapter 4. And for x of tilde of n, now this is a periodic signal. So we can apply our Fourier series technique. And it's very clean. Okay. And yeah, so this is the formula we had from chapter 3. So AK will be 1 over summation over 1 period x tilde of n, and e to the minus jk, and omega naught being 2 pi divided by n. And now this summation over 1 period. This summation over 1 period, because we think the x of n is only has a finite support between minus n1 to n2. So we can place this summation over 1 period somewhere around here, and then it can be cut off at minus n1 to n2. And yeah, so this is similar reasoning. So we can cut the summation from this part. Then if you only sign this part, then x tilde is equal to xn. Then since x of n is 0 all the outside, then it's same as signing xn from minus infinity to the infinity. So we change this x tilde to xn, then change the summation from minus infinity to the infinity. Okay? Yeah, just the same thing again. And here are the reminder for the Fourier series formula. X tilde of n equal to summation ak e to the jk omega naught n, and ak equal to 1 over summation k x tilde of n e to the minus jk omega naught n. It's very symmetric to each other. We have duality. And yeah, so ak is the summation minus infinity to infinity thing. And we write this once again. Then now we just do some change of names, and want to push n to infinity and get some integral out. And it's not too complicated. So ak is this thing. So this is just changing this formula, changing once again, just changing x tilde to x, and changing the range of summation. And now we define a new function. This is some function in terms of omega instead of k. Okay? So yeah, similar to what we do chapter 4 once again. So big X of e to the j omega. We do e to the j omega instead of j omega here because it's discrete-time, and the discrete-time eigenfunctions we always think it as some alpha to the k instead of e to the j omega t. Yeah. So yeah, sorry, it should be alpha to the t. Yeah. Yeah. Not too different. It's just a notation thing. But anyway, so this function in terms of frequency, this spectrum function, here we just give it a brute force definition. We define it as summation n minus infinity to infinity x of n e to the j minus j omega n. Okay. Then the interesting things happen. Then this ak now kind of should look like a sampling of this big X, and is it? So if we ak is have 1 over n here, so 1 over n here, And this thing, you find out that's just big X of omega equal to k omega naught, where this 2 pi divided by n is omega naught. Okay? Because you see those things are basically the same, except you have omega here and then you have k 2 pi divided by n here. Okay? So ak is just big X, sample is point k omega naught. Then we want to, okay, so we rewrite this analysis relationship in terms of our this continuous spectrum now. And now we want to rewrite this analysis relationship also in terms of our x of big X. And let's see how that happens. So we start from the original equation. So x tilde of n some ak and e to the jk omega naught n. And then we switch our ak into our big X. And yeah, so 1 over n big X and still e to the jk omega naught n. And now we do another change. That is, we switch this 1 over n as omega naught divided by 2 pi, just because omega equals 2 pi divided by n. So obviously you can switch 1 over n as something in terms of omega naught. Now we look at this equation and we see that we can approximate this summation as an integral once again. It's because if you think k omega naught is some omega, like we want to do, yeah. And now we have this x is on omega. Then this summation is this omega naught will be like d omega, and k omega naught is some point on this omega axis, and this big X of j k omega naught is some function we want to integrate over. And yeah, so this summation is really just some integration. So this summation is sum over, okay, let's go this a little slower. So this summation is like summing over a whole bunch of rectangles with complex areas. And so the height is actually a complex number. So the height will be this big X and e to the j omega n. And the width is omega naught. And you're summing over a whole bunch of these rectangles. And when you take a limit of n go to big N go to infinity, which means omega naught goes to 0, then those summation of triangles area will become the integration of this thing. Okay? And yeah, so we think of saying if we take the big N go to infinity limit, then this becomes an integral, and this 2 pi is still this 2 pi, and the area of n and this limit, the range of this k of k in a big N range, and because k omega naught is 2 pi, so this this n range, if you times 2 pi, so in terms of omega, this range is actually 2 pi. Okay, and so you will integrate over some range of 2 pi, and now those two things you can write them in terms of this continuous variable omega. So x of e to the j omega, e to the j omega n, and this omega naught becomes like a differential d omega. So any question? This is all very similar to chapter 4. Okay, yeah. So now I basically finish our derivation, and so we think as n goes to infinity, x tilde will be equal to this integral. But by our construction, we also think as n goes to infinity, x tilde will become x. So yeah, so that's what happened. So x, as n goes to infinity, x will equal to this integral in terms of big N times e to the j omega n. Okay. And so, oh, I didn't change. Okay. And yeah. And yeah, so those two equations are our Fourier transform pair for discrete time signal. So x of n equal to an integration over interval of 2 pi, big X of e to the j, big X e to the j omega times e to the j omega d omega, and also times 1 over 2 pi, and big X of e to the j omega equal to summation n minus infinity with infinity, x of n e to the minus j omega n. Okay. So once again, let's go back. It is very similar. Okay. Yeah, you see those two are very similar. So since this equation is basically the same, except the interval you're integrating over is just over 2 pi instead of over whole range of frequency, and the analysis relations are different. So you have a integral because you have discrete signal. So instead of integrating over all the time, you have summing over all the n. Okay. And anyway, so that's our two equations. We also have the comparison here again. And the 2 pi, this integration 2 pi means that you're integrating over any interval of length 2 pi. And the starting point doesn't matter because the big X is going to be periodic with period 2 pi. So you can take any starting point omega naught. And most of the time you just take omega naught equals 0. Or minus pi to pi is also good. Okay. So I think it depends on the signal, maybe sometimes from 0 to 2 pi and sometimes from minus pi to pi. Depends on which is easier for you. Okay, yeah. And just like all the Fourier things, this big X is called a spectrum. Question? And yeah, our derivation says that we derive our Fourier transform by taking big N to infinity, and another thing, we have emphasized this quite a bit of time. That is, if you have a discrete time signal, then your spectrum is something periodic with period 2 pi. And we can derive it once again here. So if you think about your big X at some point omega plus 2 pi, and then you can plug into this analysis equation, and you got extra 2 pi here, and because multiplication exponent equals, the addition exponent equals the multiplication of the exponential, and once again use this e to the 2 pi n equal to 0 because n is integer. And let's just change it back to the original thing. So derive once again, this thing is periodic once again we derive that this big X spectrum is periodic with period 2 pi. Okay. And this period 2 pi thing, we have seen that the spectrum is periodic in 2 pi, then it means that the high frequencies things are things around pi and minus pi, the odd multiple of pi and the high frequency. That's high frequency. And low frequencies are those frequency around 0 or 2 pi or minus 2 pi or those multiple of 2 pi. Okay. And here I have some example. And so if your signal like this is a little smoothing, so kind of something that has a peak, and it's a low frequency signal, then its spectrum is centered around this 0 or 2 pi. And on the other example, we have a signal that looks kind of similar. It's also centered around 0, but it keeps going negative, positive, negative, positive, negative, positive. And the negative positive thing is the highest frequency you can get for discrete-time signal. And in the frequency domain, it will correspond to something has very high frequency. Something has frequency around this pi. And remember, if the signal has frequency pi, then just keep going negative, positive, negative, positive, negative, positive. Any question? Okay. So let's see some example. Hopefully get more intuition here. Okay, so this is going to be something you better memorize the result for. And yeah, because it's quite useful. So this is exponential decay function. Okay. So in our x domain, we have our exponential decay function, and once again cut off at n equal to 0. Okay. And yeah, and one is to be convergent, so it better be an exponential decay, so the absolute value of this thing better be less than 1. Okay. And then we have our big X. Then we just apply our formula here. Okay, so we brute force calculation, apply the formula of summation. So from -infinity to infinity, our X, so that is Han-Hsuan. And then we need to apply our negative complex exponential. So it's e to the minus j omega n. And then it's brute force calculation here. So it's u of n will cut out your summation to n to 0. And you have alpha n and, okay, sorry, it's not alpha, it's a. So you have an and e to the minus j omega n. And they found out that that's just a times e to the minus j omega to the nth power. And our favorite power series. So we can use the geometric sum formula. So just 1 over 1 minus whatever this thing. Okay. And yeah, so we've done our summation. And then we can do plot. So this is going to be a complex number, so we plot it in terms of the absolute value and the angle, and and in terms of different omega. And it actually depends on, so we only say the absolute value of a is less than 0. And I guess it can be complex, but for now we think it's real. So if it's real and positive, then yeah, if it's real and positive, then it's going to be 1 minus a something. And you see that it's a little easier to see this in terms of complex pen, right? So think about, okay, let's see if I can draw this here. So think about this 1 over 1 minus a e to the minus j omega. So you can think about the denominator in terms of complex pen. So you have a 1 here. Okay, let's see if I can. This work? Okay. Pen. So complex pen here. So it's very annoying. How do I cancel that? 你知道怎么弄吗？这样子画不出来，或者是压下去它会自动跑的旋转出来。
这可能之后要再
对，还是我就画很快，他就没有时间跑选单出来。是因为 OK just draw with okay. Anyway, so this is complex plan. So we have real axis and imaginary axis, and I have one here, and we can have a circle of radius a here, right? So when yeah, it's a radius of the value of a, okay, and we know the radius is less than 1. Okay, so if a is positive, then a equal minus 0 omega star here, and as omega goes from 0 to 2 pi, then it circles this, it goes around this circle and go the whole loop from 0 to 2 pi. And you can see the distance here is smallest when omega equals 0 and biggest when omega equals 1. But you need to take the inverse, so it's actually the amplitude is highest when omega equals 0 and lowest when omega equals pi. Okay. But if a is negative, then negative real, then you start from this point and then go the whole loop of 2 pi, and you'll see the whole picture get shifted by some frequency pi. And okay, yeah. So if a is positive, then this thing is centered around low frequency, and a is negative, you see this thing is centered around high frequency. And that's fit our intuitive, right? Because if a is positive, then it's just exponential decay thing and kind of local frequency, just like in this example. And if a is negative, then this thing is going to go to this positive, negative, positive, negative, positive, negative decay. And that's also actually seen as some very high frequency signal. Question? The calculation is easy, but there are some things you can interpret it here. And yeah, you can also think about when a is not real, what happened. And other thing, okay. So other example, okay. This is very similar to the previous example, but instead of cutting off with this u of n, we put the absolute value here. So this is like to the Lorentz decay. When n is bigger than 0, then it's an exponential decay to big N, and when n is less than 0, then this becomes minus n, so it's also exponential decay, because absolute value of a is less than 1. And anyway, so seeing if I have absolute value here, and it's really you can just break this into 2 parts, because it's quite discontinuous. Well, it's discrete time, but it's very different behavior around 0. So anyway, break it into the n bigger than 0 part and the n less than 0 part, and it's discrete time, so instead of less than 0, it's down to minus 1. Okay. So anyway, so you have the same part we have from the previous example. So the summation n from 0 to infinity, and also another n from minus infinity to 1, and you can flip it around. You change n to minus n and into a better form. So that's another summation. Okay, so we actually call this minus n, but instead of from 0, you start from 1 because there's minus 1 here. So summation n from 1 to infinity, and so similar to this thing. Not that similar, because instead of minus j omega, now you have plus j omega. Yeah? Both of them have plus power in n, plus power in a. So a e to the j omega to the n. And anyway, so both of them is going to be geometry series. But this series start from 1, and this series start from because n from 0. Sorry, n is from 0, but it's m from 1, so this series actually starts from this a equal j omega. Okay, e to j omega here. And yeah, then you have two things here, and you can do a cross multiplication, and the result will be this function. Okay, and well, we can kind of see, although we haven't talked about the property, but this is assuming a is real, then this is real and even, and this is real and even. Okay, so we have nice symmetry here. And now we have the plot. Okay, so I don't. So you see this double-sided exponential decay, and now we have this real and even spectrum. Now, because it's real, then we don't need to do two plots. We just have one plot here. Okay. And it's actually centered around 0. We can, well, for a less than, for a positive. For a negative, well, it's left as an exercise. Not hard to figure out. Yeah, so you look at this, and we can check some point for cosine omega equal to 0. Okay, sorry, for omega equal to 0, then cosine omega equal to 1. So it's 1 minus a squared, and 1 minus a, and parentheses square. So actually 1 plus a over 1 over 1 minus a. Okay. Okay. Any question? Okay. Yeah. It is not too hard to see that when you change a from positive to negative, and s greater than change, s greater than change, you just get the extra negative sign here, and the other thing as shifting this cosine omega with a pi. So if you change a to positive to negative, so everything will just shift the frequency pi, and you get peaks around plus pi and minus pi, just as you expected, because that's the high frequency. Okay, and not okay, no question. Then let's go back to our favorite example of square function, wave function, once again. So xot is the square wave function from minus n1 to n1. And our frequency will kind of look like sinc function, but not quite, because it needs to be periodic. So sinc function is like sin omega over omega. But if 1 omega is not going to be periodic, so instead we have sin omega over sin omega, and just with different frequency, different constant on your omega. Okay, and but okay, so that's the result. But let's go to a derivation. Go back to a derivation a little bit. Derivation is straightforward. Summation from oh, okay, a little confused. Okay, I think we skipped most of the derivation here, but I think it's going to be we did this right. Is something similar to what we did in the periodic Fourier series. Okay, so yeah, we already did this in chapter 3 when we have a periodic discrete-time thing. And anyway, so it's going to be a summation of e to the j omega n, and from minus n1 to n1, and you can see that this is also a geometric series. Okay, so this is e to the minus j omega and the parentheses to the n. So it's a geometric series, and once again you can use the geometric series formula. And yeah, you just need to do some work to show that they are in the form of this sin omega over sin omega. And that's once again using our favorite order relationship, where you know that e to the minus j omega minus e to the plus j, sorry, e to the plus j omega minus e to the minus j omega is about sine omega. Okay. And anyway, so you plot it out, and it will look like this. And here, okay. And I guess the shape of this thing depends on how big your n1 is. And here we see that I think if you have bigger n1, then you have more peak here. So here we have a basic kind of smallest possible n1, so we have 2 peak per. Yeah, we have n1 equal to 2, and we have 2 peak per period, and yeah, probably I think the number of peak probably proportional to, yeah, sine pi, yeah, the number of peaks should be proportional to the n1 here. The number of peak per period. And anyway, so once again you see this is periodic with period 2 pi. Okay. So we go to it's a little weird. Oh, okay. Any question? If not, oh, we have 5 minutes. Oh, we can talk about convergence. Convergence is really quick, and so just like the Discrete-Time Fourier series, because it's discrete, so the convergence is a little easier. But sometimes you still have a problem. So remember our 2 formula are this. So big X is the summation from n minus infinity to infinity, and small x is from big X is the integral of 2 pi. And so there are still possibility of things being divergent, and that's because you are summing over infinite number of infinite series here. Okay? So the summation n is from minus infinity to infinity. So this big X summation might not converge. But we have 2 conditions that they will be convergent. That is, if it's absolutely summable, so the absolute value is the sum of the absolute value is finite, and or if the square of the absolute value sum over is finite, so finite energy. So if either of this is true, then this will actually converge. Okay. Okay. So that's just 2 conditions. We didn't actually give derivation here. And the other thing is this integral. Okay, so this is the integral just over a region, finite region 2 pi. So it can be divergent, but most of the time it should be okay, usually. So if you have really bad big X, obviously you integrating over integral, this can still give you trouble, but usually it's nice. So yeah, so we see that the convergence relationship of this thing is usually nice. You just need to be absolutely summable. So this is similar to the Dirichlet condition. Okay. So Dirichlet condition will also have this absolutely summable, but so for Dirichlet condition we also have the discontinuity, don't have too many discontinuity, and don't have too many maximum minima. But here we have a discrete signal, so there is no notion of discontinuity, and the number of minimum and maximum is going to be finite. So they are basically auto-satisfied, so you only need to be absolutely summable. for this to be nice. And the other condition is finite energy, and we also have something similar condition in continuous time. So that's for the convergence, and we have 2 minutes, and we can stop. I guess we cannot derive too much, but we can see really quick. So next thing we are going to talk about is the Fourier transform for periodic signal. And yeah, so we are following chapter 4, where the notion is that we derive the Fourier transform for a periodic signal, but we want to Fourier transform to encompass everything. So we also derive it for periodic signal and write them as delta functions. And so in chapter 4, we have this relationship where you have the complex exponential, you will get the Fourier transform to the delta function. And in this chapter, a similar thing will happen. So if you have a complex exponential, it's also going to get a spectrum of delta function. But now spectrum need to be always periodic with the period 2 pi. So we just repeat this delta function into the impulse train where the interval is 2 pi between them. Okay? And so what we do is we get this complex exponential is going to be transformed into this impulse train, which we can also check by just doing the inverse Fourier transform. And then we can write periodic function in the sum of periodic impulses. But we'll see this next time. So any question, or we'll stop today? Okay. Let's stop.为什么我的诶